Hello, I'm Rakesh Nadig, a PhD student in the Safari Research Group at ETH Zurich. Today I'm going to present our work, Flash Cosmos in Flash Bulk Bitwise Operations using inherent computation capability of NAND flash memory. This work was published at Micro 2022. This is the outline of my talk. I'll start by providing some motivation and discuss the key problem that we address in this work. Bulk bitwise operations are widely used computation primitives in many data-intensive applications such as databases, genome analysis, graph processing, etc. The key problem is the performance and energy efficiency of bulk bitwise operations is bottlenecked by data movement in conventional systems. We look at the data movement bottleneck in conventional systems in a bit more detail. Here we show a very high-level overview of a conventional system, which has a compute unit, main memory, and storage device. To perform simple bulk bitwise operations, massive amounts of data are transferred through the memory hierarchy to the compute units. And if the data resides in the storage device, the external I/O bandwidth of the storage device, which is lesser than the main memory bandwidth, becomes the bottleneck in conventional systems. Near data processing, or NDP in short, can effectively mitigate data movement by performing simple bitwise operations where the data resides. Here we show a few prior works which propose NDP techniques at different levels of memory hierarchy. And in this work, our focus is mainly on in-storage processing and in-flash processing because these techniques are highly effective when the data sets are quite large and do not fit in the main memory. In-storage processing uses in-storage compute units, which can be embedded cores or FPGA to send only perform the computation and send only the computation results outside the storage device. And ISP can mitigate data movement overhead by reducing the external IOs between the storage device and the host. However, in-storage processing still reads large amounts of data from the underlying flash chips to the in-storage compute units. And the internal I/O bandwidth of the storage device, which is not significantly higher than the external I/O bandwidth, becomes the main bottleneck in storage processing. So let's move the computation closer to where the data resides. And if we look at, and in flash processing, the computation is performed inside the NAND flash chips, and only the result is transferred to the in-storage compute units. So IFP fundamentally mitigates data movement. And to our knowledge, there is only one recent work called Parabit, which performs bulk bitwise operations inside NAND flash chips by intelligently controlling the latching circuit of the page buffer. And in this figure, we show a high-level organization of an NAND flash chip, which has several flash pages and a page buffer to temporarily store the data which is read or written. And in Parabit, if you want to perform bitwise AND operations of 32 operands, where each operand is stored in a flash page, the operands are read sequentially to the page buffer, and the result is accumulated in the page buffer during the sequential sensing operation. When all the operands are read sequentially, the result would be accumulated in the page buffer, and this result would be transferred out of the flash chip. And this significantly reduces the data movement. However, each sensing operation is quite expensive, and the serial sensing operations in Parabit can bottleneck the performance and energy efficiency. So there is also another limitation of Parabit, which is the reliability of computation results. It is well known that NAND flash memory is highly error prone, and in-flash processing techniques cannot leverage error correcting codes because error correction happens outside the flash chip in the flash controller. Here we see many bit errors in each operand, and these bit errors get accumulated in the result in the page buffer during the serial sensing operation. And this limits the applicability of in-flash processing to highly error tolerant applications. So our goal in this work is to address the bottleneck of in-flash processing, which is serial sensing of operands, and provide more accurate computation results and make in-flash processing reliable. So to this end, we propose Flash Cosmos. Flash Cosmos enables computation on multiple operands with a single sensing operation. And we show the same high-level organization of a flash chip. And here now we see how Flash Cosmos performs the computation. We see 32 operands stored in different flash pages, and simultaneous sensing results in a bitwise AND of 32 operands in the page buffer. And we also provide accurate computation results by eliminating raw bit errors in stored data. So next I'll give a brief background on flash memory organization that is necessary to understand our key ideas. We start with the flash cell. A flash cell stores data by adjusting the amount of charge in the cell. Here we have an erase cell which has low charge level, and this stores bit data 1. And we have a programmed cell which has high charge level, and this stores bit data 0. And when a flash cell is activated, if it's an erase cell, it operates as a resistor. If it is a programmed cell, it operates as an open switch. A set of flash cells that are serially connected forms a NAND string. And when we read a flash string, the cells that we do not want to read are called non-target cells, and they operate as resistors regardless of the stored data. And the target cells operate as resistors or open switches based on depending on the stored data. And the bitline current during a read operation passes through the NAND string if the target cell stores 1 and operates as a resistor. If the target cell stores 0 and operates as an open switch, during a read operation, the bitline current gets blocked, and this is read as 0. Several NAND strings at the same vertical position constitute a NAND flash block, and a single word line controls a large number of flash cells at the same vertical position, and this enables high bit level parallelism in NAND flash memory. And a large number of blocks share the same bit lines in the NAND flash chip. So our key observation is that if we look at a NAND flash string, the cells are connected serially, and this is similar to the digital AND logic. And if we look at multiple NAND flash strings connected to the same bit line, we can consider that they are connected in parallel, and this is similar to digital OR logic. Now, let's look at the key ideas of Flash Cosmos. In Flash Cosmos, we introduced two key techniques: multi-word line sensing, or MWS, that enables in-flash bulk bitwise operations via a single sensing operation, and enhanced SLC mode programming to eliminate raw bit errors in stored data and thus in computation results. Let's start with MWS. The key observation with MWS is that if we simultaneously activate multiple word lines in the same block, then we perform bitwise AND of stored data in the word lines. And this we call intra-block MWS. We start with an example where we read two word lines, and the other word lines are non-target cells which operate as resistors. And we read word line 1 and word line 2 simultaneously. And depending on the data stored in these cells, during a read operation, the bitline current flows through the NAND string. And here we see that in bitline 4, the current flows through the NAND string because all cells operate as resistors or store the value 1. And this is similar to the bitwise AND of the target cells. And this principle can also be extended to more than two word lines. And here we see four word lines where in each NAND string, there is a cell which operates as an open switch. And during the MWS operation, the bitline current gets blocked through the NAND string, and the result is 0. So this is again similar to the bitwise AND of the target cells. So intra-block MWS enables bitwise AND of multiple pages in the same block via a single sensing operation. Next, we look at simultaneously activating multiple word lines in different blocks, which results in bitwise OR of the stored data in the word lines. And here we show an example with two word lines in different blocks. And when we simultaneously activate these two word lines, depending on the data stored in these in the target cells in the NAND strings, we can either see result being 1 or 0. If the result is 1, then that is because of a flash cell which operates as a resistor. And in case of bit line 4, where the target NAND strings uh, have open switches, the result is a 0, which is similar to bitwise OR of the target cells. Next, this principle can also be extended for 3 word lines. And here we see that if there is a single target cell which operates as a resistor, the result would be 1. And the bit line reads as 0 only when all the target cells are 0. And this is again similar to bitwise OR of the target cells. So interblock MWS enables bitwise OR of multiple pages in different blocks via a single sensing operation. So in Flash Cosmos, we also support other types of bitwise operations, not NAND, XOR, etc., by leveraging existing features of NAND flash memory. And I would encourage everyone to go through the paper for more details. So next we look at enhanced SLC mode programming, which eliminates raw bit errors in stored data. And the goal of ESP is to eliminate raw bit errors in the stored data and the computation results. And to achieve this, we program only a single bit per cell, which is similar to the SLC mode programming. And this trades storage density for reliability. And ESP also performs more precise programming of the cells, which trades programming latency for reliable computation. So ESP maximizes the reliability margin between the different states of the flash cells. And ESP enables reliable in-flash computation by trading storage density and programming latency. And these overheads affect only data used in in-flash computation. Next, we look at the evaluation of Flash Cosmos. We evaluate Flash Cosmos in 2 ways. We first perform a real device characterization to validate the feasibility and reliability of Flash Cosmos. And this is done using 160 3D NAND flash chips. And we also use worst case operating conditions to perform the real device characterization. Next, we look at a system level evaluation, where we use MQSIM, a state-of-the-art SSD simulator, and 3 real-world applications. And Flash Cosmos is compared with 3 baselines: a conventional system which uses a multi-core CPU to perform bulk bitwise operations, an in-storage processing unit where which uses a hardware accelerator to perform computation within the storage device, and Parabit, which is the state-of-the-art in flash processing mechanism. The results of the real device characterization show that both intra and interblock MWS require no changes to cell array of commodity NAND flash chips. Both MWS operations can activate multiple word lines at the same time with small increase in sensing latency. And ESP significantly improves the reliability of computation results, and we observe 0-bit errors in the tested flash cells. Next, we look at the results from the system level evaluation. We show the performance and energy efficiency of Flash Cosmos and the baselines. Here we show the performance in terms of speed up over the conventional system and energy efficiency over the conventional system. Flash Cosmos provides significant performance and energy benefits over the baselines. And the larger the number of operands, the higher the performance and energy efficiency benefits of Flash Cosmos over the other computing platforms. So we have a lot more results and analysis in the paper. We describe the optimizations to improve the performance of bulk bitwise operations, and we also provide details on the new flash commands and the interfaces to enable Flash Cosmos at a system level, and also describe the overhead analysis. Here is a link to the paper. I would encourage everyone to go through the paper. In summary, Flash Cosmos is the first work that enables in-flash multi-operand bulk bitwise operations with a single sensing operation and at high reliability. Flash Cosmos significantly improves performance and energy efficiency over the baselines. And the benefits of Flash Cosmos come at a very low cost and requires no changes to flash cell arrays. Finally, I would like to mention about our SSD course. This is a projects and seminar course where we discuss SSD basics and advanced topics, and we also provide hands-on research exploration and discuss cutting edge research in storage systems and SSDs. This is the current iteration of the course. We also offer processing and memory course with short weekly lectures and hands-on projects. This is the current iteration of the course and the previous iteration. We also organize real PIM tutorials in top conferences. And here are the details of the recent PIM tutorials. This is in ISCA 2023, ASPLOS 2023, and HPCA. And we also have an upcoming real PIM tutorial at Micro 2023. And I would encourage everyone to attend this tutorial and learn about real world processing in memory systems for modern workloads. I would like to end my presentation here. Thank you for your patience, and I hope this presentation was interesting to you. Thank you.